You're in the Romans for the last talk of the day. Here will be Backdoors by Ruben Santamarta. All right, thank you, and there you go.
Okay, hello everybody. I'm really glad to be here today. I'm sure you are enjoying Black Hat, so I hope that you enjoy this talk as well. My name is Ruben Santamarta. I work as a security researcher for IOActive. Today I'm presenting here the Backdoors, a journey into the secrets of industrial firmware. What is this talk about? Well, basically it's about reverse engineering, mainly applied to the research of industrial firmware. But the problem is that I don't have access to those devices. I don't have access to physical access to those devices. So I had to come up with an approach to get over this little issue. There are some reasons why you can face the scenario of not having access to an industrial device. Mainly, probably one of the most important reasons is money. Those devices usually are pretty expensive, so it's difficult to access one of those. But there are additional reasons. For example, some of those devices are subjected to restrictions due to commercial reasons, even due to security concerns. For example, in the nuclear industry, you can guess that some of those devices that are implemented or deployed in industrial facilities are not accessible to the public. Another reason, maybe a special case I faced some time ago while doing a pen test against an industrial facility where I couldn't even have access to the PLCs, but still you have to present results. I mean, it's your job. You have been hired for something. So I decided to make an approach, to build an approach to analyze, to research into industrial devices without having the actual device. During this talk, I present some vulnerabilities that are actual backdoors. I'm a software researcher, not a hardware one, so I wasn't used to finding backdoors in the software, but once I began to research into the industrial world, it's amazing because it's pretty common to find backdoors in all those industrial devices that control critical infrastructures. I think it's awesome. What is this talk not about? Well, it's not about spreading fear. I mean, I'm only presenting technical details. Everyone can verify them within a controlled environment. I'm not interested in talking about my opinions on this matter. It's not important. I mean, I have an opinion. I do have an opinion on this topic, but it's not important. Let me briefly introduce the context of the situation. Maybe a decade ago, the security and the context where the industrial control systems were living was in balance, because obviously industrial control systems have been there for years, and we weren't too used to hearing about explosions. They had their problems like any other complex system, but I mean, hearing news about uranium enrichment facilities or something like that is something new for us. So at the present day, the context has dramatically changed. Almost any modern PLC has a built-in web server, exposes some of its functionality through a web browser. You can access a PLC through a web browser. You can control a power plant or a water treatment plant with a mobile phone. So obviously, a lot of attack vectors have been added. So the problem is that the context has grown, and the security is not in balance right now. And I think that that gap, that difference between the context and the security is what an attacker can use against those systems. But I'm not here to talk about geopolitics or whatever, but reversing. So if we are planning to find vulnerabilities in or backdoors in industrial devices, we need at least four things mainly. Either, I mean, you need this program. There is no option. And some other common tools, for example, a hex editor or a compiler, nothing very special. We need the firmware. There is no option as well. And hopefully, you can access the software that vendors usually provide to end customers, or to end users, to customers, to configure or control the devices. We can extract a lot of information from both the firmware and software. We also need documentation, but all the documentation we can collect about the target, about the device, but not only or not strictly related with the device, but also with those third parties implementing or deploying that device, because this will help us to better build the whole picture of the device, because we have to remember that we don't have access to the actual device. And finally, it's optional, the target device. In this case, we have no access to those devices, but maybe in Shodan or in ERIP, you can find some of them exposed. Obviously time, but I think it's not a problem. To illustrate the overall idea behind the reasoning of this approach, let me show you a very basic example. I mean, it has nothing really, but I think it's pretty interesting for the reasoning. Some time ago, I was reading an advisory from a friend of mine who found an injection in a server. In this case, it was a server from Samsung, an HVAC server, which stands for heating, ventilation, air conditioning. And well, the advisory states that you have to update the firmware, but I was curious about how you can do that. I spent some time reading documentation. I couldn't be able to find any reference to authentication during the process. So, okay, I thought that, well, they are not using authentication, so what they are using. So at that moment, I had two options. Maybe I could ask support staff, but it didn't seem a good option because I wasn't even a customer. So the other options was reversing the updater software. So you can guess which option I chose. 5 minutes later, there is little to add. I mean, the updater was a Java program, and you can decompile without any problem. And the issue is that they were using a hard-coded account, so you can access those devices via telnet as root. It's not bad. I mean, it's a very simple example, but it is very useful to illustrate the overall idea. Maybe too much security through obscurity. Right. When researching into the firmware, one of the things you have to do is identifying all the important things. Sometimes the firmware is a single binary image. You start with a single binary image, but then you find a bootloader, you find a compressed operating system, then you find another compressed blob inside the operating system, and so on. So, as a security researcher, you're probably only interested in a small piece of the firmware. So I see the whole process as those nested Russian dolls called Matroska. So there are different levels of complication. So what we have to do is identifying several key points. As I just said, one of the most important things is the firmware itself. Usually you find a binary image, which is comprised of a header plus additional data. You can extract useful information from the header. It depends on the firmware, obviously, but for example, we can usually extract information such as the version, the operating system they are using, maybe checksums, maybe even base addresses. Well, another interesting point is the magic bytes. Well, probably all of you know a well-known tool called Bingwalk. It detects embedded content into binary image by looking for byte patterns. Even in the case of using Bingwalk, you should memorize some common byte patterns, because I mean, it's a great tool, but according to my experience, it fails sometimes. So you can completely trust the output of this tool. For example, you should memorize byte patterns for common compression algorithms, because you probably need to manually analyze a binary image. Another interesting point is file systems. If you can identify a file system inside a binary image, you have a lot of information you can extract a lot of information from that. You can usually identify those patterns by strings or magic bytes. Bingwalk also does a really good job on finding these patterns, but still, it's highly recommended to memorize the patterns by your own, because it sometimes fails. You can't reverse anything if you don't know the platform the firmware was built for. So one of the things you have to do is identifying the platform. It's not a big deal. You can quickly identify the opcodes. There is a really good presentation from Igor Skoczynski from Hexrace that collects almost any byte pattern out there for almost any platform or common platform used in embedded systems. Another interesting point, high entropy zones. Usually high entropy zones mean that there are something interesting, for example, something compressed or something encrypted. So there are some tools out there. For example, there are some Python scripts, an IDA plugin, if I remember well. For example, in this case, I'm presenting the output of a great tool, which is called Radar, and it can detect, it can calculate the entropy of the blocks. And one of the most fruitful source of information in firmware is the strings. You can extract information about almost anything from logic, from libraries used. You can identify almost anything, but the problem is that you have a lot of strings in a binary image, so you have to spend some time analyzing them. So the basic approach would be something as follows. The first thing you have to do is identify compressed blobs, because usually that means there are something important, some parts important behind those compressed blobs. You can use bin walk or any other means we have just mentioned. You can also extract information from the header or the entropy zones. Then, once you have identified compressed blobs that are subjected to be reversed, you should identify the platform and you should identify the base address of that blob. To do so, there are some tricks. You can, if you are lucky enough, you can extract that information from the bootloader, but maybe the compressed blob is a bootloader. It's a bootloader itself, so you have to find the base address of the bootloader as well. Sometimes the header contains the base address where the blob or where the operating system is gonna be loaded. But generally, there are a couple of tricks I found interesting because they are working very well. The first one is the load immediate instructions, and the second one is the switch statements. You have to, basically this trick consists of a very simple approach. You have to find a switch statement with a jump table with absolute addresses, and then you have to match every entry address in the jump table to the case. And once you have done that, Then you have to subtract the entry address from the jump table to the offset where the case is, and then you have the base address. Then you have to detect functions. One of the problems I faced when loading firmware into IDA was the lack of detection of some functions. So, well, it's not a big deal. You have to, you can create a Python script or an IDC script. I've got an IDC script available in my website, at my website, if you want to check it out, to detect patterns. Finally, you should be able to rebuild symbols. It depends on the operating system, but for example, in the case of VxWorks, there is a way to rebuild the symbol table in a generic way, because usually you find the symbol table embedded in the image. We'll see an example just in a couple of minutes. Then there are other options. For example, recently a researcher demonstrated how you can identify libc functions by statistic methods, Aníbal Sacco. You can also rebuild symbols by manually match C source code to assembly. We'll see some examples. And finally, if you can't apply these tricks, you can try to find well-structured patterns, because sometimes symbol tables look like a well-structured byte pattern. So let's see how all this boring theory looks in real life. Siemens Scalance is the first device we are going to demo today. It's an industrial Ethernet switch. It's based on VxWorks for ARM. And we are going to see how to reconstruct symbols. We are going to see how analyze the firmware. We are going to extract information from a built-in web server, some VxWorks systems have. And once we have done all of this, we are going to demonstrate how to find a hidden, undocumented account. In this case, unfortunately or fortunately, is disabled by default. So, but I think it's interesting, the whole process. So you can freely download the firmware from Siemens website. And the first thing you see is that header, like we have just talking about. We can find that they are using VxWorks, the version, and after some bytes, we can find something pretty common, an ELF header. So, well, in this case, the task is simple. We have to remove the previous bytes, and then we have an ELF. Okay, this is the main routine in the ELF. You can see, pay attention with that value, because it's the entry point where this bootloader is gonna jump, yeah, just right after decompressing the compressed blob it contains. In this case, we can see how, okay. If we take a look at the strings, we can clearly identify strings which are commonly used by compression algorithms. So in this case, we can also apply the approach of matching C source code to assembly, because, for example, if we identify the compression algorithm and it's open source, we can download the library implementation, and then it takes time, but it works. You have to match the C source code to the assembly, and then you start to rebuild symbols step by step. And you can see how the control is transferred here. So it's not very complex, just a common routine. You see that the entry point was stored at that variable. And once we have identified the compressed blob, the ELF decompressed, we can load it into IDA, and we start to detect functions. You can see that all these undefined areas can be detected as functions when we have run our IDC script. It takes some time. We are not going to see how it ends, but you see here how the functions are being created. So we have advanced a step into rebuilding the whole framework. Then we are going to reconstruct symbols. As we saw before, in the case of VxWorks-based firmwares, you can follow a generic way to reconstruct symbols. You can identify the symbol table because it has a well-structured byte pattern, but there is another way which is pretty easy. There is a function that reconstructs the symbol table. So you have to find that string and find the cross reference, and then it's a simple loop. So you have to look at these values. This is where the symbol table begins, and this is where the symbol table ends. In all the VxWorks systems, this function is pretty much the same. So we are going to see how to rebuild symbols. This is where the symbol table begins. And in a couple of seconds, we'll see how the functions get renamed to the symbol. Okay, you can see this is completely awesome in the sense not in the sense that you can extract a lot of information. It changes the whole experience of reversing a firmware. If you have the symbols, you can reverse a firmware with a lot of accuracy. So you can see a lot of, I mean, the symbols names by themselves provide a lot of information. So if you are able to rebuild a symbol table, or even if you are able to partially rebuild symbols, you can expect good results in your reversing task. And this is the name of the function. Once we have rebuilt the symbols, that function gets renamed as well. The name is user. You can see. Okay. And once we have the symbol table parsed and revealed, we can begin to research into the firmware actually. We are going to see a demo. If you take a look at the authentication routines, the authentication functions, something caught my attention. In every authentication function, there was a logic that distinguishes between any name and debug name. For example, in this one, you can see that there is a specific check for a username, which is debug, and after this check, there is a function which is intended to apparently to check whether this firmware is a release image, and then there is another function to check whether this debug login is enabled. Unfortunately, this account is disabled by default, but I think it's pretty interesting to find those kind of things. This approach is pretty much the same that I followed to find the backdoors in the Schneider quantum, in the Schneider modicum modules. It was a VxWorks based system as well. It had the symbols table, so it was pretty much the same. According to the documentation from Siemens, these devices have two accounts enabled by default. One of them is admin, the password for that account is admin, and the other one is user. The password is also user. So once we have the symbols, we can find how those accounts are actually initialized. You can see here that the admin account is initialized, and then the user account, but there is another account that gets initialized. The debug account with a password ELS debug. Another interesting point is that, for example, we can find hard-coded keys. In this case, Siemens Scalance encrypts some values, encrypts some files, and apparently they are using Blowfish to encrypt those values. If we take a look at the cross-reference from Blowfish init, you can see that it's used by several functions. So we can find the key used to encrypt those values. For example, in this case is ELS key. Let's imagine that we can find a vulnerability to grab some file, an arbitrary file from the device. We should be able to decrypt that file if it's encrypted, or okay. And then the last step to analyze this firmware is to extract information from a custom file system which belongs to the WinWeb server, which is a built-in web server. Some VxWorks, well, most of the VxWorks-based system have. VxWorks provides a tool called PagePack. So with this tool, you can create a C source code file which contains all the files the developer wants to share through the web server. Then those files end up in the binary image, in the firmware. So this web server, or this file system, this web server uses a file system that doesn't require an actual file system. It lies in the non-volatile memory, so it's called mem file system. And it's a very simple file system. It's comprised of a signature, but you can completely trust that signature because it can be defined at compile time. So maybe it's a better idea to find the well-structured byte patterns. Then after this signature, we can find the header, which contains a couple of fields. The first one apparently is some kind of version, and the second one is the number of files, the number of entries that the file system contains. Right after the header, we can find the first entry. Every entry has its own structure, which is comprised of a name, a 64 bytes field. Then, after the name, including the path, if applicable, there is a length field, and finally the offset from the beginning of the embedded file system, where we can find the data for the file. So we are going to see how to extract all those files from that file server. First, for example, if we take a look at all those functions beginning with HTTP, we can find some additional entry points to test the security of the device, since this device is exposing its function or some of its functionality through a web server. In this case, you can find some URLs. You should try. And then we are going to extract the file system. If you take a look here, all this undefined area is the embedded file system, the MEM file system. And as we have just seen, it contains the signature, the version field, and the number of entries. Right after that field, we can find the first entry, which is an HTML file. You can see how the files are being extracted. I mean, it's not very complex. All you have to do is parsing the file system with the structures I previously explained. But it's very interesting because you are obtaining all those web page or web files, all those scripts or whatever the developer wants to serve. We are basically reconstructing the whole firmware. We have revealed the symbol table, we have revealed the symbols, we have extracted information from the main file system. We can take a look at some of the files we have just extracted. For example, in this case, the private MID file. This file is available at the Siemens website, so in this case, it's not pretty interesting. And we are going to see another example. In this case, it's a device, an industrial serial server from Advantech. In this case, we are going to see a different approach. It's the firmware, it's a custom Red Boot with a custom RAM disk. So we have to try to reconstruct the RAM disk, and we have to try to decompress it. In order to do so, we are going to analyze the routine that decompress the RAM disk. Then we are going to reconstruct partially symbols, because this firmware doesn't contain a symbol table, but we can we can reconstruct symbols by matching C to assembly. And finally, we are going to emulate the binaries contained in the RAM disk by using QEMU. This is pretty awesome because you are emulating the binaries that are running in the device without having the actual device. So you can try to find vulnerabilities in the device just by having the firmware. We are going to see some demos. This is the binary image we obtained from the vendor's website. You can see some strings that provides useful information, for example, the boot script, and you can see how the different compressed blobs inside the redboot are defined. You can see the load, the address where the image is located. You can see the size. So you can easily extract those compressed blobs. You see where the compressed blob begins. And by analyzing the firmware, by also reconstructing the symbols by matching C-source code to assembly, we have identified that this firmware was using LZO as a compression algorithm. So you have to download the open source implementation of LZO, and then you have to match the C-source code to the assembly. This is a routine that decompresses the blob. And pay attention to that value, because this firmware contains a custom RAM disk. So one of the things we have to do is trying to figure out what is the structure of the RAM disk. Once we have extracted a RAM disk, you can see here, there is 5 bytes here, header, and then after that header, you can find the previous value, which is the size of the original chunk. I mean, the original RAM disk has been cut into other chunks, and every chunk has been compressed with LZO, and then all those chunks have been put together. So the structure is the original size. Then after this value, we can find the compressed size. And then there is a Shilley checksum, which is the sum of all the bytes of the chunk. So we create a program to parse and extract and decompress to reveal the original RAM disk. Now it's done. We have the original RAM disk. So now we are able to analyze the contents of the RAM disk. You can see some strings, the VCBox. In order to emulate the binaries from a platform, a different platform, you have to follow some steps. In this specific case, we need to enlarge our RAM disk, because we have to copy to the RAM disk the binary from QEMU. So as usual, we create a new RAM disk via mknode, etc., and copy the original contents of the RAM disk. We have just decompressed to the new one, and then we have a larger RAM disk we can use to emulate the binaries. The next thing you have to do is to set up a cross-compile environment in order to compile QEMU with specific features. For example, you have to compile QEMU statically. You have to compile QEMU with debug stubs. You have to enable the support to additional formats in the kernel, and then you have to copy the libs you can find in the RAM disk to a specific directory from the installation of QEMU. Then you can mount this new RAM disk, and you can emulate the binaries contained in it. We can see a demo. This is the QEMU binary we have to copy to the RAM disk. Then we chroot. And now we can execute any binary the original RAM disk contains. Obviously, we can work the contents of the binary as well. For example, we can find a private key left behind on the firmware, so you can find interesting things. Also a password, root default concretely. You can explore the contents without any problem. And we are going to see the main point of the talk. In this case, it's a pretty interesting case because we can find almost every example of what we have been talking about. It's a backdoor I found in a family of smart meters from Schneider. We are going to see how we can find documentation. This case has a firmware backdoor, has a software backdoor. These smart meters have remote access enabled by default, and we finally we'll finally see how some confidential documents from Schneider were exposed publicly. So basically, I decided to take a look at those smart meters. So I collected information. I was reading all the documentation, and I found this sentence. Factory access is restricted to Schneider Electric technical support, etc., etc. It reminds me, for example, when you are a child and someone tells you you can touch that shiny, cute, and very expensive thing, but you are a child, so you have to touch that thing. Probably you'll break it as well. So as a security researcher, it's pretty much the same. It's something like a call for papers. So I decided I had to research into these meters. basically, some of these meters can be used as a revenue smart meters, and those smart meters come locked from factory, so you can modify your bill, unfortunately. So there are two different logins, two different accounts. The regular login, which provides the customer basic functionality, and the factory login, which it's the real target. So quickly, the binary is a very simple file, an S record, where we can obtain some information. It's an ASCII representation of the binary. Again, we rebase the firmware by looking at the load immediate instructions. We detect functions, and we end up rebuilding symbols. No symbol table, but again, some strings which lead to manually reconstruct symbols. I found the implementation of this malloc in a Chinese website, so yeah, it's pretty awesome. Basically, the image, the binary image, is a bootloader and the compressed OS. Once we have the compressed, the OS, we can analyze them without any problem. So I was looking at the strings, and I found setting backdoor password to so well. I mean, there is little to add. So yeah, it's a backdoor password, but I mean, I don't have the device, so I just guessing how the backdoor password is generated. So I was tracking where that string was used, and there was a comparison against 14 bytes, and it's curious because the telnet server that those smart meters expose, the prompt contains a serial number which is 14 bytes. So if you are generating a backdoor password for a device, it makes sense. You have to use a unique ID. So it makes sense. The serial seems a good option. So yeah, it's a backdoor password. It generates a number based on the serial number, and another string I won't disclose by vendor's request. It doesn't matter. The algorithm is simple. You see in C source code, but the curious thing is about what I found in the software the Schneider provided to end customers to configure and control the smart meter. It turns out there is a backdoor also in the software. We are going to see quickly because there is little time. So there is a menu in this software which it's disabled by default. But you can enable by pressing the control key when clicking into the menu, or by modifying a version number which is embedded in the binary. So there is another backdoor, because if you enable this dialog by pressing the control key, the software asks you for a factory code, incorrect access code. So we are going to pose like a fake meter in order to receive from the software the backdoor password, because My point is that software has been used by the Schneider support staff to troubleshooting customers, and the same version with some capabilities disabled was deployed to the public. So, well, the factory code doesn't matter because we can just set a breakpoint before the comparison against the right code and use that code. And then the software is going to try to access the factory login to extract some information. So we are receiving the login, the regular login, and after that, the program is trying to do the factory login with the backdoor password. Which is this one. So in this way, I could be able to check that my initial guess was correct. Then factory access granted. So now we have complete control over the smart meter. We can remove the hardware lock, so we can modify our bill. We can do whatever we want. Okay, so I'm gonna finish. The last thing, I decided to search for the user login, and what I found was an open FTP server containing confidential documents from Schneider where the backdoor functionality was detailed. Obviously, I contacted ICS CERT, Schneider, everybody gets involved. Google removed, after a few hours from the cache, the FTP server. Schneider acknowledged the backdoor, and a new set of firmwares is ready. Some of them are being deployed. Due to the nature of the flow, it might be considered a forever day. Just 3 conclusions. I hope someone can use this info to better secure their devices. I hope someone can use this info to research into other devices. Finally, I hope someday both of them share that research somewhere. Thank you so much for coming. Have fun. You can contact me anytime at rubens@iactive.com or reverse mode.